Hello, everybody. So we are moving on with our limits discussion, and today we're going to talk about infinite limits and limits at infinity. So what we're going to look at is we're going to look at how to calculate infinite limits, look at locating all your vertical asymptotes, calculating limits at infinity, and finding horizontal asymptotes. So we're bringing back in our Haas and Vaz that we learned last year when we did our graphic analysis. But before we move on, we need to talk about something called indeterminate forms. So basically, when you have a rational function, sometimes you have the ability to be able to look at it and say, oh, it has a limit, or oh, it may not have a limit. Whereas in like a polynomial, you always know that there's going to be a limit because we're going to be approaching something from the left and the right side. Well, in an indeterminate form, we may or may not have a limit because something might happen there. So it's important to note that there are restrictions on some of the limit properties. So for instance, if a particular limit as x approaches c of r of x is equal to 0, then finding this limit here, that one right there, may present difficult since the denominator would be 0. So basically this is saying if you took this polynomial here and you looked at C and you found the limit, the answer could be 0, but then you're putting it in a fraction form. Well, now you have a problem because your denominator is 0 and you can't have a 0 in the denominator. So there's things that you would have to do. You'd have to look at, well, is it an asymptote or is it a whole or what's going on with it that would allow me to hopefully still might be able to find some sort of limit. The other thing that could happen is if you have two different functions, f of x and g of x, and you put them over each other and then find the specific limit, you could wind up where the top and the bottom both go to 0. That gets you something that looks like a 0 over 0. And so there's a couple of things that you could actually do here. This is actually a pretty good deal. If you get something where you wind up with f of x is over to 0, that's kind of not of a good thing because you may not be able to do anything with that, which means you're going to wind up with not having a limit. But at least if you have something that looks like this, where both of your top and bottom wind up with 0 over 0, you could do some algebra, cancel things out, and rerun the limit at that specific number and actually come up with an answer. So going forward, because we're going to be looking at a lot of rational equations here, going forward, you need to realize that just because your denominator is 0 does it not necessarily mean that you're going to have a limit that does not exist, because you still could have a limit that exists, especially if you wind up in that form. Okay? So let's move on. Infinite limits. What does that mean? Well, infinite limits basically means as you approach a specific number, so your number in question, as you approach that number, you are actually approaching the vertical asymptote. So when you're looking at a specific limit and you are running towards a number, you're going to have an actual limit answer. But if you're looking at a limit and it's running towards an asymptote, either, left bound, right bound, or both, then you have a limit that doesn't exist because it's going off either into a positive infinity or negative infinity. So this is going back to what I just said a few seconds ago in that indeterminate form. This means you have something that kind of looks like the form of that. You have some of rational functions that your bottom has gone to 0, but your numerator it didn't cancel out. And so you wound up with something over 0. And that's something that you can't have when you're dealing with limits. And if that happens, you wind up with an actual infinite limit. Okay. So what we're going to do now is we have these specific things that happen here. So the function f of x will have a vertical asymptote at x equals, in this case, a, if we obtain any, and that is the key word here. It's any of these. So if I get one of them, it's going to be true for all of them. So the limit as x approaches a from the positive side. So that means when you're looking at this, we are coming, if this is a here, right there, that's really big, I don't like that. If we're approaching a from this side and it shoots up or down in either direction, that is what this is talking about. Okay. From the left side, the same thing, except now we're coming from the left-hand side. So there's that. Here's our A again. And now we're coming from this side. I can either do something like this, or I could do something like that. If that happens, then again, you're going to positive and negative infinity, which basically means if you're looking at the graph as a whole, as one big picture, you could have something that looks like this piece here, where you're approaching infinity on both sides. And so that's what this is talking about, is that if you approach it from the positive and it's positive or negative infinity, that's going to be your answer. You're approaching it from the left side and it has positive or negative infinity, that's going to be your answer. They all go together. So f of x increases without bound as x approaches c. So this is pretty much like the visual of what I was just talking about. As we're approaching it, it's going up, 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 up. It's never, ever, ever going to touch c, but we get closer and closer and closer, so it's constantly changing. And so we don't have a consistent or a pattern type y value. It goes 10, 100, 1,000, 10,000, so on and so on and so on, and it'll never, ever, ever, ever stop. If you have like the TI Nspire, I think you probably can do it with the 84. I have to play around with it and see. But if you zoom in to the C value and you have something that looks like this, you will see that what's happening is that it starts to oscillate a whole lot because you're going and going and going and going. And that's another one of the reasons why it makes it not existing or going off into infinity. And so in this case, we are increasing here without bound. And remember, you can also decrease without bound. So it'd be basically coming down in this direction, doing the same thing. All right, so that's increasing without bound. That is decreasing without bound. Okay. Increasing, obviously, you're going out to positive and positive infinity. And then decreasing, you're going to negative infinity. Now, you can have multiple asymptotes in this. You can have, depending on what you're focusing on, you can have multiple answers. So like on this one, I plug in a +1 or a -1. So if I'm looking here, I'm going further and further south on this one. And then as I come over here to +1, I'm going northbound. So I'm going up to positive infinity on both. And so if you're trying to figure out, okay, well, if I have a calculator, this is going to be easy because I can look at it. But what happens if I don't have a calculator? If you don't have a calculator, just do what you can. And if you take a notice, so we know that at 1, for instance, I get 1 over 0, so I have a D in E. But if I plug in like 0.5, so if I plug in 1/2, for instance, so that's going to take me over to here. You will notice that back over here, and I plug in the 1/2, I wind up with 1/2 over, so 1/4 minus 1, so that'd be, we're going to square this, 1/2 over, so that's 9 over 16. So we have 1/2 times 16 over 9. So it'd be 8/9. And if you take a look at this, and I told you sometimes you may not have a calculator, you're trying to figure out, well, how do I know without a calculator if this is actually going to do? You can keep backing it up and take a look at it, but this is one of the reasons why we started off the way we did, talking about an indeterminate form. If I plug in that 1, you have to notice that this did not go to 0. The bottom did, but your numerator did not. And since it did not go to 0, you know you have something here that doesn't exist. So what you need to, so really the only thing that you're trying to figure out from this point here is, how do I know if it's going to be, if I'm going towards positive infinity and negative infinity? And that's where you take a look at the numbers around it. Am I getting consistently bigger, or am I getting consistently smaller as I'm approaching? Because as long as you're increasing, then you know that you're going to be going up towards infinity. But if you decrease in value, you have negative numbers, then you're going down to negative infinity. Okay. Again, with one-sided limits, you have the same thing. So I can only look at it approaching it from the right side. I can only look at it approaching it from the left side, or the right side. And so you can have that ability. So this is approaching it the right side, going positive, right side going negative. And then left side going positive, left side going negative. So one-sided limits is literally what it says. You're just looking at the one side. When you put this into the calculator, your calculator, for whatever reason, when it has an asymptote, it does not draw like a dashed line or anything else like that. It actually draws a solid line. So you need to realize that when you're doing this, even though this is a solid line, this is not really there. There's nothing there because it does not exist. It's just showing you on the calculator that this is actually what you're approaching, and this is what your graph is actually doing. So, determining infinite limits. When you're doing this, so you need to figure out the denominator, where is it going to be equal to 0? So if your limit number down here, when you plug it in, winds up being 0, and your numerator is not a 0, you will have an asymptote. So you're going to have a VA on that one. The question is, the main question, and what they'll ask you on the AP exam, is going to be this one right here. Yeah, I know we're approaching a vertical asymptote, but am I going off to positive infinity or negative infinity? And that's where you build a table. And if you don't have a calculator, use numbers that'll work for you. If you do have a calculator, then it's easy. You just put it in there and take a look at it. Okay. This piece here, use your calculator to make sure. You may not always have a calculator. But if you do, that's the easiest way. If not, you kind of need to know how to sketch these by hand. So that's something else you needed if you're not really too sure about. Maybe, spend 20 minutes a day, find some really weird looking graph or whatever, and see if you can just kind of sketch it by hand and see what actually winds up happening. Okay. So we talked about that one. So again, the infinite limits. So this is kind of like your parent here. This is your parent when it comes to the basis of infinite limits. So this one has, when you're approaching it from the left, you're going down, and when you're approaching it right, you're going up. And so that's what it's talking about, because if it asks you for one side or the other, you can have the left side going down to negative infinity, but you could have the right side going up. Either way, the limit still doesn't exist. Either way. But if it's asking you for an infinite answer, you're going to have to go in there and say, okay, am I going negative, or am I going to go more positive? And so these are the options of what it's talking about. So when we go into these and we start talking about bounds and everything else with just infinity, this is talking about in behavior. This right here is talking about looking at a specific number. So you need to be aware that this piece right here is really critical into looking at what our focus needs to be. Because as long as it's a number, we are actually going to be focusing on that number. But if it ever gives you this piece here where we're running off into infinity, that's something that's a little different. We're going to be talking about that here in a moment. Okay. So remove this. Looking at this, remember how I told you that this was your parent right here? This is 1 over x. So when you have this, when you have 1 over x squared, notice that it has the same characteristics. So you are still, because this is based off of the actual 1 over x model, you're still going to have those as your actual answers. The question is, am I going up to positive or am I going down to negative? That's going to be the question that you're always going to have to answer when it comes to these. So now we want to find out if the limit here does exist. So I know if I take this negative 4 or this 4 and I'm approaching it from the left-hand side, I know when I plug this in, I'm going to get a very, 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 very small number. And so as I start doing this and I'm looking at this, I know that as I put my numbers in that I'm eventually going to go all the way, I'm going to be going down towards negative infinity. And so if you actually take a look at the actual graph, you can start wherever you want to go. And if you notice, as you start to approach something, we are actually not approaching anything, but our numbers keep changing. Our Y values keep changing. They just keep getting bigger. So that's the other thing to take a look at. And so we know that when we plug in this case, 3.999 minus 4, we get an answer that this is going to be a really small number. So I know since this is a really small number and my numerator did not go to 0, I know that it's going to be infinity. But what, and so you were like, well, but how? I don't understand. You know it's going to a negative infinity because of this piece here. This 3.999 is smaller than that 4, so this is going to be a very small negative number. Notice I don't care what the number is, to be completely honest with you. Because whatever I put down here, I'm more concerned about the sign. Because if I put a number down there, because my top is going to stay whatever my top is going to be. It's the bottom piece that I have to worry about. And so I need to know, well, am I going down positive or negative? And so since I plug in 3.999 and it's smaller than 4, I've got a number that's going towards infinity. I'm sorry, it's going towards negative, which means I already know that this is going to be a 1 over something. So this is going to be a 1 over 0 type question. So that means I'm going to have an infinity as an answer. Now I just have to narrow it down more. Is it positive or negative? So if I go to the left side of negative 4, I'm sorry, the left side of positive 4, then I'm looking at something that's smaller than that. And so that's why it's a negative. Okay. So let's see. Same thing here. So this wants to know the actual limit overall. So if I plug in a 1, I'm going to wind up again with that 1 over 0 piece. Okay. So now you have to take a look at the left and look at the right so you can determine exactly if your overall limit will exist. So here is where the wording gets tricky. Because if both of your limits go towards positive infinity, you can actually answer this question as positive infinity or negative infinity. It still doesn't exist because you're not approaching a specific number, but you can still have an infinity-based answer. What we want to know is what's happening as I'm approaching this 1. from the left side, and what's happening as I approach this one from the right side, am I going to wind up approaching both positive infinity or both negative infinity, or am I going to go one way and then turn around and go the other direction? Because if I have one going to negative infinity and one going to positive infinity, then I wind up with the complete does not exist, a D and E. So I want to take a look at my left side. I wind up going to a negative infinity. I take a look at the right side, I'm going up to positive infinity. So I've got something that looks like this right here. So that means when I actually take a look at this, this one flat out does not exist. Unlike the one behind it, this one actually had an infinity answer, because I was only first off looking at it from one side, but it actually had an infinity answer. This one will actually be does not exist, and you can look by looking at the graph, or you can plug in numbers to be able to see this. Okay, so yes, infinity still means it doesn't exist. However, you can take that does not exist and say, okay, yeah, fine, it doesn't exist, but do I still go in the same direction? For this question, the answer is no, we don't go in the same direction. We go in two opposite different directions. So when you are checking for your vertical asymptotes and to find out what's happening and everything else, there's 4 different things to look at. So the first thing you want to do is you want to let a number, like when you plug in your C value, if you get a number, then you will actually have an actual limit. So you're able to substitute that in and you actually get a limit. So one of your possibilities as an answer will be your actual limit that you get. The other is if you have 0 over anything, that's what the K is for. The K means anything. I have 0 over 15, 0 over -3, 0 over 1/4. 0 over anything means that your limit will actually be equal to 0 on this. This is where we were just talking about all these infinity type things, where if it goes to positive or negative infinity, you could have that answer. Or if you're going, one's going positive, left's going positive, right's going positive, or vice versa, and then the other one's going the opposite direction, then you have what's called does not exist. And then the fourth way to look at it is if you have a 0 over 0, this means that you could still possibly have an actual limit. So this 0 over 0 says, okay, do some algebra. Can you cross things out and maybe you have a hole, and then you can reevaluate and see if you actually have an answer at that specific point. So when you're looking at limits, you can look at it either graph, you can look at it at making a table, or substitution. If you substitute, you're looking for these 4 different things. I know that was a lot, and I know that sometimes you might have to go back and rewatch or redo or reread or whatever else. But once you start doing these problems or whatever, you'll be able to see, okay, this makes sense. I understand what's going on. I recommend you going into Delta Math. I do have some limits at infinity questions in there that will talk to you about how, or not talk to you about it, but like show you or give you problems that will give you one of these 4 type of topics and answers here as well. Okay. So now that was talking about limits that go to infinity. But what about limits at infinity? So let's go forth and look at what happens instead of having x approaches a specific number. Let's go look at your end behaviors. We talked about this a few slides back. So now let's take a look at that and see what that means. So the infinity symbol is a symbol to describe the behavior of limits that do not exist. Okay, so if I have as x approaches c, and we wind up with our graph going towards that vertical asymptote, then we have a limit that does not exist. But what it also can do is, instead of having as x approaches c, we can actually have x approaching infinity. And so what that means is, okay, so now we're not looking at a specific point. When I see that infinity, I automatically think in behavior. And when I think in behavior, the first thing that should come to your head is horizontal asymptotes or your HAs. Okay, so your horizontal asymptotes are what your end behaviors are going to do. So basically, remember, you have the 4 options that we talked about of how as x approaches positive infinity, your y is going to do 2 things. And as x approaches negative infinity, your y's are going to do 2 things. I'll show you what I mean. I'll come back to that. We'll come back to that. Give me a second. Oh, maybe not. You know what? We'll just keep on, and we'll get to that in a second. So sorry about that. So the reason this question's here is because there's something specific about a polynomial. And if you remember polynomials are just like 15x to the 17th minus 3x to the 4th plus 2x squared minus 1. Those are, they're not over anything. They're just polynomials. Doesn't matter. If you have that and you're running off into infinity, your answer is going to be either positive infinity or negative infinity, because you're not bounded anywhere. Your rational functions typically tend to be bounded, but your polynomials will never be bounded. They're going to, go off into positive infinity or negative infinity. So if it's a polynomial, then one of these 2 answers here is going to actually be your answer, depending on which way that it's asking you to go. So when we talk about limits at infinity, we need to talk about horizontal asymptotes. And so this is what this means. As I'm approaching negative infinity, what is my graph doing? Is it coming down to a horizontal asymptote and running off towards that horizontal asymptote? Same thing on the positive side. And so if you take a look here, I have this graph. These 2 lines right here, this one right here and this one down here, those are my asymptotes. And how do I know this? Because if I take a look at my graph is going off and it's doing something like this, and then it's leveling off again, which means I'm running along something. And as I'm running along something, and as I'm going off into that positive infinity in that direction over there, so if I go this way, if I take a look at this, I'm running along that line of that one value. So as my limit, as x goes to infinity of whatever this f of x function is for this one, I am actually approaching positive 1. If I'm looking at this direction here and I'm following this along, and if I notice down here, I know as my limit, as x approaches negative infinity, so I'm going off in foreverness of f of x. Oops, that's in the wrong spot. Let's try that again. Negative infinity of f of x. That's going to run off into negative 1. And so we're running off down here. We're leveling off down here. Okay. So what we're going to do, we're going to focus on rational functions, because that tends to be where a lot of your horizontal asymptotes are at, is in your rational functions. Now, I know this looks a lot scarier than, actually what it really is. But what you're focusing on is that you have basically a polynomial over a polynomial. What's nice about horizontal asymptotes is that we don't care about all of this back here. This to us doesn't really care. All we care about is our lead exponent in the front. We want the highest exponent on the top and the lowest exponent on the bottom. And that's why we only focus on this piece right here, because this is going to tell us what our graph is actually going to wind up doing. So if I take a look at this, you will notice right here that I have this graph, and it's starting off running along 1/2, and then it's going to bounce up and come back down. But as I go out to negative or positive infinity, I'm approaching that 1 1/2, or that 1.5 again. And if you take a look at it over here, I've got a polynomial over a polynomial. So where this comes from is the following. I told you I don't care about that, and I don't care about that. I only care about the highest exponents on each of them. And so if you take a look at it, something special happens, and I don't think I talked about it there. Something special happens when you have, in this case, we have 3x squared over 2x squared. Notice how both of my exponents here are exactly the same number. That's a good thing, because if both of my exponents are the exact same number, then I can cancel out the variables here, and I'm left with 3 over 2, which is that piece there. So when you're looking at these and you're looking for your horizontal asymptotes, when you're trying to figure out what they are, you only want to look at the lead coefficients. If their exponents are exactly the same, then we ignore that and we only look at their coefficients, and that will actually tell you what your horizontal asymptote will actually be. Okay? Let's see here. So let's take a look at, why do I have a blank screen here? I have a blank screen here, and I don't know why. Our three options. So you're only looking at the lead exponents on the top and the bottom. So the first one, if your top exponent is higher than your bottom exponent, then you're either going to go off to positive infinity or negative infinity. Okay? If your bottom exponent is bigger than your top, then you're going to have a horizontal asymptote at y equals 0, which means basically your graph is going to run along the x-axis. Okay? If your exponent here and here are exactly the same, we ignore those, and it's just simply, you're going to cancel out this piece, and it's simply whatever your fraction is here in the front. So basically what that's saying is, if I have ax to the m over bx to the n, and we're looking at number 3 here, is saying that I can cancel out that, and that leaves me with a over b, and that will be my horizontal asymptote. So take a second and look at these two here, and let's see if you can figure out, do I have any horizontal asymptotes here? And if I do, what it is. If you don't have a horizontal asymptote, then tell me that you are going off into positive infinity or negative infinity. Okay, so pause the video, see if you can figure out what your horizontal asymptotes are, if any, and then when you start back up, we'll go over the problems with you. All right, welcome back. So we're going to take a look at the first one here. So again, I told you, I don't care about this piece at all here or here. So I'm only going to focus on that right there. So I take a look at, first off, my exponents. Well, my exponent, my m, is smaller than my n value. And so that was number 2. And if that happens, that means that I have a horizontal asymptote. I have a HA at y equals 0. So the limit for f of x, the limit for, oh my goodness, the limit for this of f of x is going to be 0. And it's going to be true as my x approaches infinity. And it's also going to be true as my x approaches negative infinity. Okay. On the second one, you will notice that I have a 2x to the fifth over x to the third. So my m is bigger than my n. So I have an infinity thing here. So what you need to do is you need to look at it from the left and right side. So my limit as x goes off into infinity of f of x, and then my limit as x goes off to negative infinity of this f of x. So if I plug in, I don't know, let's say 10. Well, oh, do I have a calculator in this thing? Oh, I do. Yay. So I have 2 times 10 to the fifth power. Okay. And then I have divided by 10 to the third power. So that gives me a positive number. So I know that I'm going to wind up with infinity on that one. So then I do the same thing, not the calendar. I do the same thing here. Now I'm going to go off to the negative one. 10, let's go negative 10. So 2 times, do I have a negative? Yeah, there it is. Negative 10. And we're going to raise that to the fifth power. And I'm going to divide that by 2 times negative 10. I'm going to raise that to the third power. Oh, let me try that again. I think I did something wrong. Because it wasn't 2. My bad. Let's clear that. Go 10 raised to the third. It's negative. So I have a negative over negative, which is a positive. So this is going to run off to positive infinity. So now you're like, well, are we sure about that? If you have a calculator, you'd plug this into your calculator and actually look at how the graph is going. So basically what's happening is that you have this graph, and as your x is going this way, your graph is going off into that direction, and as your x is going this way, then your graph is going to go off into that direction. And why does that make sense? Well, if you look at this, if I simplify this, I wind up with an x squared graph. Well, an x squared graph is a parabola. And so in my parabola, I've got this U-shaped here. So I go off to positive infinity or off to negative infinity. Okay. Now, rational functions, we just got finished talking about. There are a couple of other different types of functions that you may see that will also have a limit, but you won't know these until you graph these. So let's look at this first one here. So I have this 5 plus sine of x over the square root of x. So if you take a notice of this, this is not oscillating. First off, this is being very wavy. But if you notice, my wave is getting closer and closer and closer to that number 5 right there. Since my wave is dying down and is becoming closer and closer to this 5 right here, I have a horizontal asymptote at 5. So this would be a question that you would put into your calculator. So this would be a graphing calculator question. So this would be on the actual the calculator portion of your exam. Okay, because people are not they're not going to expect you to know what that looks like. Okay. The other one is you could have, this is another calculator question one. So you're going to plug this in and notice that you can run along the lines down here. And then you can run along the lines that up here going off into that direction. So, and notice how this here actually crosses the horizontal asymptote. That's okay, because you can cross the horizontal asymptote, but then you can rise back up to it and run along the line. That is okay. That is something that you're allowed to do, because we are more concerned about what's happening at infinity and not what's happening at numbers around 10 or 20. We're talking big numbers out to like the hundreds and the thousands, so we can see what's actually going on. Okay. So recap: if you have an infinite limit, when you have approaching from the left, you're going to infinity. Approaching right, you're going to infinity. That means your whole entire thing is going to run off into infinity, one way or the other. Or you have a specific limit at infinity. If you do this, you are looking for horizontal asymptotes here. So we want to make sure that when you are looking for horizontal asymptotes, that you want to know, am I going to be running along the x-axis? Am I actually going to be running along something? Or do I actually really not have a horizontal asymptote and I'm running out to being unbounded? So that's going to be when you see this one right here. So these are just 5 things just to kind of give you a reminder on what we did. So when the limit of a function at some x value is approaching positive or negative infinity, then the function has a horizontal asymptote at that value. Number 2, to find a horizontal asymptote, you should find the limit as x approaches positive or minus infinity. Number 3, a horizontal asymptote occurs at y equals 0 when the degree of the denominator is greater than the degree of the numerator. Number 4, a limit does not exist when the degree of the numerator is greater. Basically, you have no horizontal asymptote. And then number 5, a horizontal asymptote occurs at the ratio of the leading coefficients when the highest degree terms are equal. So this just goes back over the actual horizontal piece of it to kind of clear that up for you. So that brings us to the end of limits at infinity. So what you're going to need to do now is log into Delta Math and do some practice problems if you need that extra help or whatever. Don't forget you got Khan Academy as well that you can use. The quizzes only and the tests only are going to be due for Khan Academy, but there are practice problems in Khan Academy that will help you. Your homework is actually posted in Google Classroom, so if there are no questions, which obviously there's not because I'm actually recording this, so sorry about that. So if you need me, there we go. Send me a remind question, send me an email, make sure you attach your work to it so I can see what you're talking about. Or if you need, me to log in and work with you one-on-one, let me know that too. If you have specific questions, we can do that during my conference period, which is 8:20 to 9:20. Or we can set up a time later in the evening or something. I can sit down with you for 10 or 15 minutes and go over it. Or if there's time in your 5th period class, I can sit down with you one-on-one and go over this as well. So please, please, please make sure you are asking me questions. Please don't get behind on this and get frustrated because you're not really sure on what's going on. All right. So I hope this wasn't as bad as it felt like it was for me, because I felt like I made a lot of mistakes, but hopefully I corrected them. So have a good day. I will talk to you soon. TTFN. Ta-ta for now.